How are you? Is your mute on?
No. Yep, there we go.
How are you doing?
I'm good. How are you?
Good.
Yes, I'm
I
ready.
am so happy to see your face.
How was your trip?
It was good. It was exhausting and unexpected, but it was good. I'm really glad we went, and I'm grateful that we got the chance to go. So,
I'm glad you guys were able to come back.
that's
I'm glad you all were able to come back.
yeah. Danny, is your video on that one?
Yes, it
There we
should
go.
be. Yeah.
Yep, I can see you.
Yay. I just had to change my view. How are you, Danny?
I'm doing all right. I'm in my childhood bedroom, which is a trip, but
I believe it.
we will make it.
Yep.
Well, at least you get to do fun chemistry in your bedroom.
I do. I'm so excited.
Yeah, I'll be surprised if two toddlers don't run behind me. So if they
That's
do,
okay.
Yeah.
I think we'll manage.
yeah,
No.
decided to start babysitting right
Oh,
during
yeah.
the time. So I was like, well, I need an hour where I can study, but
Yeah, no, my grumpy 16-year-old sister may come in at some point and want something. So just ignore her.
That's okay.
we'll say hi.
We're
We'll
all
stop
doing
the
the
class
best
and
we
teach
can
her.
with what we've got right now.
Yeah.
So, Carolyn, where are you?
I'm currently in Knoxville.
Okay.
I came to spend the weekend at Diego's, and then the whole quarantine thing happened. So now I'm here. But I got a babysitting job and just stayed here.
How are your parents doing with you being so far away?
They're good. My mom can't leave the house, so because she's more prone to get it. So
Yeah.
she's just really bored, which means we call a lot. But it's good.
That's a good thing. Good morning, Cameron.
Hello.
Where's Cameron? I can't see. Oh, there's more
Wait.
people.
So, Cameron, where are you?
I am in my new study. I cleaned out older rooms. My dad is a photographer, so we have a studio in my house. We don't use it anymore, so I cleaned it out, and now it's I'm calling it my laboratory, actually. But
I like it.
we're just yet.
Danny, I love that your walls are pink. It makes me think of you as a kid.
Yeah. 5-year-old me. I wanted my walls to be pink and then I regretted it immediately after. So
Now you're stuck.
now I'm stuck. Though
There are worse
hopefully
things you could be stuck with.
Yes. Neon yellow was a thing for a while. Yeah. No, it's bad.
Oh man, it's good to see you guys. I miss you all.
Yeah, no, I'm
gonna be
about to
like-
go nuts.
You got a whole lot longer before you're allowed to go nuts, Danny.
I know.
I'm sorry. It's okay. I'm gonna work remotely.
Is it raining where you all are today?
Yes, a lot.
Yeah, it's gross.
Yeah, it's kind of yuck.
Hi,
What's happened?
Cody. I'm just stuck here.
I'm
You know,
comfortable with the head in the corner. So what is this, Zoom or?
Yeah, this is Zoom. We've still got a few minutes before we actually start. But I figured we'd catch up for a little
That is a very pink room.
bit.
It is. Kind of makes me nauseous a little bit.
Hi,
But we'll be
Leah.
okay.
All right, I gotta go back to work.
Yeah.
Yay.
Okay, please. So Leah, are you in your childhood bedroom as well?
Well, not quite because me and my mom moved about 2 years ago. So,
Oh,
but I'm in
A little
my
bit more adult than baby
I'm in
Danny.
my college bedroom.
There you go. I like it.
Yes.
Well, we will give everybody about 6 more minutes before we actually start. but I'm so glad to see you guys. This whole let's go online thing has been fun.
Yeah.
At
How
least
are
you
the
know how
rest
to
of your
use Zoom.
classes handling it?
Not well. Well, some of them. My humanities professor doesn't understand the internet yet.
Good.
So we're not actually having classes anymore.
Isaac, welcome.
So,
Oh, there's Cam McConnell. Hi, Cam. Cameron McConnell is connecting to audio. It's trying.
Oh, there she is.
French toast?
Yes, please.
Syrup and powdered sugar?
Uh-huh.
Love you.
Come say hi.
Ahead of what?
This is my OChem professor. Hi, this is Dee.
Hi.
She brought me French toast.
Oh,
So,
sweet of you.
I know. All right, bye, babe.
Cameron McConnell, how are you?
I'm great. My puppy is here, but she's outside.
Aw.
Mom was like, I'll take her outside during your meeting because she doesn't need to lay in the floor and bark.
Aw, is she perfect in every way?
Yes, she is so sweet. She's really not much of a puppy. Like, she's little, but she just sleeps and just wants to sit in your lap. I'm sure the puppy stage will get here, but for now, we're like, okay.
Yeah.
Carolyn's seen about 1,000 pictures of her.
It makes my day.
So Cameron, is all of your family home now?
Yes. My brother's downstairs Zooming his teacher. I'm up here. My mom's in the garage and my dad's in the basement.
Perfect. Social isolation at its best.
Yes.
Does anybody have any family that is out of the country or unable to be reached at the moment? I know, Carolyn, your family's out of the country.
Yep. But they're good, so I'm good.
That's good. Hi, Amy and Andrea.
Okay, I think we figured it out. Okay.
Alicia.
Hi. Wait, I can't hear you. You have a unmute. Wait, there we
Can you
go.
hear me now, Amy?
Wait, say something.
Can you hear me now?
Okay. Okay, I'm gonna head out. Okay, we're good.
Andrea.
Just say bye. Bye.
Good morning, Alicia.
Oh, it's loading. Something's loading.
Something's always loading in Zoom. This is normal. There she is. You got to unmute yourself, Alicia.
Hello.
Hello. First of all, how's your ankle doing?
I got the boot off.
Yay.
Yep, I've been doing physical therapy for the past week and it's getting better.
Good. That's good to hear. Are you going to be able to keep doing physical therapy with all of these restrictions, or?
We'll see. They haven't shut down yet. So,
Okay.
but I don't know.
Well, we take it one day at a time at this point.
Yeah.
Let's see. We got 2 more minutes before class technically starts. So I'll do my normal announcing stuff. If you all want to mute your microphone so that we don't get some feedback, if you have a question or something, feel free to unmute your microphone and get my attention. But just so that we don't get a whole lot of feedback, that's the easiest way to do this. So first of all, I am so happy to see all of you. I cannot tell you how awful it has been to not see you for a week. It's been terrible. And I miss you all a lot. And I'm really glad we get to do this live class because it's, first of all, I think going to be a little bit easier for you to ask questions as we go, just like you would in class. But it'll also be a a chance for us to be together. So that'll be awesome too. So the way this is going to work moving forward, we are going to, oh my gosh, you're all here. Everybody's here. You guys just made my day. You made my day. Okay, so the way this is going to work moving from here on out, obviously we're going to finish the semester online. That's been communicated already. And that does mean we have to change a few things. Labs are obviously going to be not really a thing. There's a few, Sam, I know you're so disappointed by that. There's a few things that we're going to be able to do virtually, like the lab you've seen on Canvas already this week. But there's also going to be some other things we're going to do. So for example, next week, I'm going to give you a scientific article on COVID-19 and ask you to read it and then kind of parse down the information like you'd be able to tell it to a family member. And then kind of compare and contrast what you've heard about COVID-19 and what's actually science. So that one's going to be a lab, but not really a lab. So we just kind of have to run with what we've got. For the rest of them, I don't know. We're flying by the seat of our pants here, and it's going to be just fine. Because we had 3 class periods dedicated to green chemistry presentations, I am going to be able to slow down lecture just a little bit. What I would like you all to do, Cameron's very happy about that. What I would like you all to do for your green chemistry presentations is you're going to give a Zoom presentation just like this, and you'll be able to share your screen like I'm going to do today, and your face will be up in the corner, and you'll be dressed professionally, at least from here up, and you'll be able to present your presentation just like you would in class. And then what I'm going to ask everybody to do is go back and watch everyone's presentation. So rather than take class time to do those presentations, we'll do those virtually recorded and you can watch them at your leisure. That does mean I get 3 class periods back, which is good, because we lost 3 last week. So your 3rd exam right now, I think, is scheduled for 2 Wednesdays from now, or 2 weeks from this Wednesday. I'm going to move that. I'm going to move it back probably to the next Monday. The way that's going to work is you will be able to download the exam. And if you have a printer, you can print it out. If not, you can just use a blank sheet of paper and, number 1, true, correction this, number 2, this, correction, short answer, all that stuff. And then what you're going to do is re-upload that exam, whether it's on a printed copy or whether it's on a piece of paper. You'll upload your answers as your exam, and then I'll grade it from there. If you want to see your second exam, I can upload those for you. I'll email them straight to you. Just drop me an email and say, hey, I want to see my second exam. I'll also put the key up online so that you guys can see what I was looking for some of those answers. Overall, I was pretty happy with the second exam. I did give you a 10-point curve, mostly out of pity that I wasn't there to answer your questions. So you're welcome. Yay, okay. So let's see, other things we need to talk about. We covered lab, this is lecture, welcome to lecture. We'll move the exam. Green chemistry, if you have not emailed me yet saying you need help finding things, you've gotta do it like yesterday, because that date is not gonna change. Your green chemistry stuff is still due on April 14th. That's a hard deadline, because I'm then going to give you a certain amount of time to record your presentation, and then I'll have to give you till the end of probably regular semester, so not including the finals week, to watch everybody else's presentation and write something out that you've watched them and blah, blah, blah. So does anybody have any questions on stuff moving forward? If you do, just unmute your mic and yell. No? Okay. Smile pretty. Okay. I just want proof that you were all here and that you all had smiling faces, even though this is, you know, the middle of a global pandemic and the world as we know it is, I don't know. We'll figure it out as we go. So, all right, today we are starting chapter 13. So if you looked on Canvas, you saw that there was a PDF of a bunch of papers for this particular, let's see if I can share my screen correctly. Here we go. Nope, that's not what I wanted. There. Okay, so this is the PDF that was up on Canvas. So it starts with this electromagnetic radiation stuff, and this actually contains one, so this part here, this structure IR matching, can everybody see this okay? Just give me a thumbs up if you can. Okay, awesome. So this structure IR spectrum matching, this is a worksheet that you guys will use as practice for matching IRs to their structures. And yes, I know this looks foreign right now. Leah, your face is like, what is this? This will make more sense as we go, I promise. But I'm just trying to walk you through this packet. Some of these, like this one, are slides that I'll show you as we go through. You'll need to memorize these tables, but I promise it's not as bad as it looks right now. We'll talk about it. The spin-spin splitting patterns is one of those kind of in-class worksheets we would have done. But this is a way for you to familiarize yourself with proton NMR, and we'll get to that when we get there, but I'm just trying to walk you through what's here. This Clues for Solving NMR Problems page is something I've written out to help you. This is one when we get to NMR, you're going to want to read this pretty thoroughly and make sure that you understand what's going on. Another slide. Okay, the last 4 or 5 sheets of this are what your take-home exam is going to look like for exam 3, okay? So I'm gonna give you an IR, an NMR, probably a carbon NMR, potentially a mass spec, which we'll talk about. And what you have to give me from this is the structure of the compound, okay? This will be completely open note, open book, just no internet. But this is to give you practice of what you're going to be doing on your take-home part of the 3rd exam. So that takes you to the end of this PDF. So I'm going to pull up my PowerPoint here on my handy-dandy tablet that Milligan was so kind to give me, because now I can actually annotate this as we go, which is helpful. So, raise your hand if you've seen this thing before. Yeah, okay, so this is not new. This is what's called the electromagnetic spectrum, okay? And remember that light has both properties of particles and waves, so it's a little bit weird, it's a little bit strange. The things you want to take notice of here are the fact that you have long wavelengths, short wavelengths, and that those are inversely related to frequency. So short wavelength is high frequency, long wavelength is low frequency. All of the types of light that you see in here, so microwaves heat up your food, but they also use what are called microwaves to heat up your food. The infrared section is one we're going to be using quite a bit. This is abbreviated as IR light, and you'll see that when we do IR spectra, those use infrared light. We'll also use ultraviolet and visible just a little bit. X-rays, of course, when you get an X-ray, that's X-rays that are being shot through your body. And then gamma rays, of course, turn you into the Hulk. The particles that we're talking about here of light are referred to as photons. And again, those have an energy, and those are referred to as quantum. So you've heard of quantized energy states probably in physics. And if this is taking you back to flashbacks of physics, I'm really sorry. But the energy of a photon, E, is proportional to frequency. So E equals h nu, where h is Planck's constant and nu is the frequency. So energy is directly related to frequency. The range of these photon energies is called the electromagnetic spectrum, which is what you're seeing in front of you. Energy is directly proportional to frequency. So where's my energy? Here. So high energy, long wavelength, low frequency. And frequency is inversely proportional to wavelength. So like I said earlier, low frequency, long wavelength. When we look at, sorry, I need to switch screens again. I'm going to be switching screens a lot here. So just, I'm sorry for making you go back and forth. Okay. So when we look at energy states, and by the way, this is 13.2. What determines whether electromagnetic radiation is absorbed by a molecule or reflected by a molecule? So there's three things. Well, the only thing that really matters is that the energy of the photon must equal the energy difference between two states. So there's three different things that we actually look at to determine what a molecule actually looks like. So we can look at nuclear spin states. We can look at vibrational states. And we can look at electronic states. For nuclear spin states, we look at something called NMR, or nuclear magnetic resonance. For vibrational states, we look at IR, or infrared, directly in the infrared region of light. And for electronic states, we look at something called UV-Vis, or ultraviolet visible spectroscopy. In molecular spectroscopy, so this thing that we're talking about with all of these acronyms, spectroscopy, I can spell today, all of these are called spectroscopy. In spectroscopy, we're concerned with the transfer of energy from a photon to a molecule. And what that helps us understand is what something looks like. So does it have a benzene ring? On that benzene ring, where are the molecules attached? Are they O to each other? Are they P to each other? These can actually tell us. That's how we know what molecules look like. Only certain energies are possible for these nuclear, vibrational, and electronic states. And these possible energies are said to be quantized. So we've looked at energy states before. If we have increasing energy going up this side here, the energy difference that we're looking at for this to actually be absorbed by a molecule is the difference between E1 and E2. So delta E is equal to E2 minus E1. Normally, there are more molecules down here in the energy 1 state, the lower energy state. That should make sense from everything we've talked about. The excitation of a photon, for example, from E1 to E2, that requires energy. And it requires this much energy, that change in energy. We also know from what we talked about on the last slide that energy is equal to h nu, which means there's a specific frequency of light that can actually make this change. When electromagnetic radiation excites a molecule, only that with the frequency with the energy that's equal to delta E is absorbed. So we're talking about light being absorbed by a molecule, and it has to have a specific frequency in order to do so. In spectroscopy, we have these things called spectrometers. Spectrometers are designed to measure the absorption of electromagnetic radiation by a sample. So if IR light is absorbed by a sample, an IR spectrometer is going to measure how much of that light was absorbed. The relationship between frequency and absorbance is plotted as a spectrum. So you'll hear me talk about an IR spectra or an IR spectrum. That's that graph that you're going to see here in just a second that shows you how much energy was absorbed in a particular sample. This consists of a series of peaks at characteristic frequencies. So every spectra that you see is going to have some sort of frequency and absorbance, and sometimes those are flipped, but you'll see those as we go. And what it's going to look like is a series of peaks and valleys, and each of those peaks and valleys means something. And these are at characteristic frequencies, and so we can attribute those to certain functional groups and certain other things that we care about. So why did this not stay where I wanted? There we go. So this second figure that you see in the packet that I gave you is infrared spectroscopies. This is IR spectroscopy. IR spectroscopy is particularly useful for identifying functional groups. This is based on vibrational states. So remember how we talked about nuclear spin states, vibrational states, and UV vis states? This one is based on vibration. So remember that all atoms in a molecule vibrate with respect to the bonds that they share. So this, unfortunately, is one of the lectures that everyone loves to watch because you get to watch me dance. Okay, it's really not dancing, but I want to show you what these molecules do. So you've probably seen some videos online of, you know, CO2 going like this, and basically what you have to think of is, think of me like water. Okay, so this is the O and these are my two H's. Okay, and I'm gonna have to stand up because I can't do this sitting down. Okay, so molecules vibrate and rotate in several different ways. The first way that they can do is they can stretch. So they can stretch symmetrically or asymmetrically. Cameron Higgins, quit laughing at me. They can also bend. So molecules can bend in a scissoring motion like this. They can bend in a rocking motion like this. They can wag like this. And they can twist like this, okay? So molecules can move in all sorts of ways. And what IR spectroscopy takes into account is the amplitude of that vibration. So if a molecule is able to vibrate, and in most cases they are, you can actually tell what functional group your molecule has based on where in the spectra you get a peak. So, a few things you need to know about IR. Instead of the units of frequency, IR uses wave numbers. Wave numbers are inverse wavelength, so they're expressed in inverse centimeters. Wave numbers are directly proportional to energy, so your highest energy is here at 4,000 wave numbers, and your lowest energy is here at 500 wave numbers. There's a table that you'll see in your packet. This is table 13.3, and this is IR absorption frequencies of common functional groups. So if you have an OH group, for example, it could be in an alcohol or in a carboxylic acid. If it's in an alcohol, it's going to show up between 3,200 and 3,600 wave numbers. And if it's in a carboxylic acids, it's going to show up between 2,500 and 3,600. Now, obviously, you can see that there's some overlap here between the two OH groups, but the way that you can tell the difference is that in alcohols, the OH peak is very broad. And what I mean by that is it's going to look more like that rather than a sharp peak. So broad peaks are characteristic of alcohols. You can see in this chart and in the next slide that there are so many different things that you can look for. And you can actually get pretty specific in IR. You can see the difference between a cis alkene and a trans alkene. You can see the difference between a triple bond C and a triple bond N. You can even see the difference between where things are substituted on a benzene ring. Now, if you're sitting there going, I have to memorize all this, she's crazy. Trust me when I tell you that the more you use these, the more they get easier to understand. And we'll look at a few of these here in just a second. I do want to go back here for just a second and explain what this fingerprint region is all about. So the part of an IR spectra that is most useful to you is this functional groups region. The fingerprint region, the pattern varies most from compound to compound, but this section usually looks a lot like this, while this section looks a little bit more like that. This is a lot easier to understand than that is. Now, I'm not saying this fingerprint region isn't helpful, because it is, and sometimes that's the only way you can distinguish between like a cis double bond or a trans double bond. But this part here is a lot easier to look at and to understand. IR spectra, let's go here. IR spectra can be obtained from solid, liquid, or gas. So you can use any type of state to get a spectra. And the way that these look, they're actually upside down of what we would expect. Because on the x-axis is your wave numbers in inverse centimeters. And on the y-axis is percent transmittance. So if you've ever worked with a Spec 450 before, You'll know that absorbance and percent transmittance are directly opposite of each other. The peaks on this particular spectra are upside down. So we call that a peak. And we call, for example, that a valley. Current IRs use what is called attenuated total reflectance with a Fourier transform of the data to give you this whole spectra from usually 4,000 wave numbers to 500. So 4,000 over there, 500 over there. It gives you that whole spectrum in seconds. So it's very, very easy to get IR spectra. And IR is actually what you guys were gonna do with all of your samples from the semester of lab. So we have an IR upstairs, and you were gonna go up and get the IR of each of your samples, which is why you were keeping them. But now that's not possible, so we'll figure something else out. One of the things that usually confuses people is the length of these peaks. So when we look at an actual IR, you'll see this, but the peaks tend to be more intense, larger, when the change in a molecular dipole moment occurs between two atoms of different electronegativity. So for example, that would be more likely a CO change, whereas this one here would be more likely a carbon-carbon change. And we're talking vibrational states here. So remember, this isn't changing from a carbon to an oxygen, but it's the vibration and rotation between the carbon and the oxygen. So I would like to take a look at this PDF again. We're gonna go all the way back up here. If you have that packet in front of you, or if you can pull it up on Canvas, that would probably be helpful. So these are IRs. This is what they look like. So what you are gonna do in this packet here, and this packet starts at structure IR spectrum matching, you're gonna take these structures here, and they're all structures of drugs, and I would like you to try to figure out which one matches to which IR spectra. So you want to look for characteristic things. Where the fingerprint region ends and where your actual helpful region starts is at about 1500. So you want to start looking right about here at 1500, and you want to go this way towards the 4000. There are some characteristic peaks that you will be able to identify easily. So for example, this peak at 1700, it's always sharp. It is always characteristic of, and I can't write on my screen right now, sadly, but this peak right here is always characteristic of a C double bond O. So that means you could have an ester, you could have an amide, you could have a ketone, you could have an aldehyde. You have a C double bond O. That's all that tells you right now. It doesn't tell you where it is in the molecule. It just tells you that you have one. If you look at this chart one page up, you'll see that these are kind of the major functional groups. This is by no means exhaustive, but it should help you look at specific parts of a molecule and be able to identify which ones of these go with the IR spectra in question. So, who has access to this document right now? Okay, most of us. All right. If you don't have it pulled up on your computer or somewhere where you can look at it, go ahead and pull it up for me. If you have it printed out, go ahead and pull it up. What I'd like you to do is look at, you can do this one of two ways. You can either start with the molecule and try to find what parts of the IR match to it, or you can start with the IR and then go backwards to the molecule. I think it's easier to start with the IR and go backwards to the molecule, but it's up to you. All of this stuff that we're doing with spectroscopy is like a puzzle. So you're trying to put puzzle pieces together. And if you hate puzzles, I'm really sorry, but it's a puzzle. So don't get frustrated by it, but it might take some time to look at pieces and try to figure out which one goes where. So what I would like you to do, I'm going to give you 5 minutes. I would like you to see if you can figure out which molecules belong to just letters A, B, and C on the IR spectra. So you're looking at page, I don't know what page now. These 3. I want to know what molecules line up with these 3 IR spectra. Cameron, quit laughing at me. So I would like you all to unmute your microphones so that you can ask questions, so that you can look through some of the stuff we've talked about already. I know it kind of seems like I'm throwing you in the deep end a little bit, but you can't understand this stuff until you try it and until you struggle with it a little bit. It's one of those things that I can't just put up on a board and teach you. So unmute your microphones and try A, B, and C. See if you can figure out which molecules line up with A, B, and C. Isaac, what's that face for?
Just thinking.
On letter B, when there's 2 peaks that look like the double bond O, does that mean there's 2 double bond O's, or
Sometimes
they-
yes, sometimes no.
Okay.
In this case, yes, there are 2 on that one.
Would that be it in amide or no?
It could be. So if you're looking at letter B, those 2 little peaks around 3,000, tend to be what are called twin peaks of NH2. So there's probably an NH2 somewhere in the molecule, which means it could be an amide, but it might not have to be. Does that make sense?
I was saying the one by the C double bond O.
So this one right here.
Yeah.
So these, I would consider both of those at about 1700. And so, like Carolyn said, there would probably be 2 C double bond O's in a molecule.
So when we're looking at this and like measuring where they fall on the spectra, are we starting with wherever it starts to dip, or are we looking at like the point for where we're in our range? So like, is it like the point that is our range, or is it like where it starts?
Yeah, those ranges are really big. So what you want to look at is kind of in what range does that one fall? And typically I look at like the bottom of the peak to see where it falls, mostly because that's closest to where I can see the numbers. but but it really doesn't matter. I mean, just pick kind of the middle of the peak. Anybody think they got a guess for any of them?
Is A ibuprofen?
A is not ibuprofen.
Is it acetaminophen?
3 is ibuprofen.
Ooh. Hmm.
Which one did you say was ibuprofen?
It's not A, but one of the 3 on this first page is.
Would it be C?
Yes. What makes you think that, Carolyn?
Well, I have answers for the other 2. So it had to be
so
something
process
else.
elimination. That's good. Let's look at C for a second. So if you look at the structure of ibuprofen, you're going to be looking for a carboxylic acid and a benzene ring, maybe. And if you can find the benzene ring, you're going to have to find that the functional groups are para to each other. So what evidence do you see in letter C for a carboxylic acid?
So the OH for carboxylic acids is typically 2,400 to 3,400.
Mm-hmm.
So it's in the range.
Yeah, so there's stuff in that range.
So if you look at, if you can flip or scroll and look at letter F for me, this is what I mean by broad, okay? So this OH peak here is responsible for an alcohol. This one in letter C is much sharper, okay? So that is a carboxylic acid OH. What's the other thing that you can find in this spectra that points you to a carboxylic acid?
Isn't the C double bond O peak within that range down by like the 60?
That guy right there. So that one at 1700 is a C double bond O. So there's 2 things that you can find for sure that point you to the fact that this is a carboxylic acid. The C double bond O and the not as broad OH peak. Now there are things you could find in this fingerprint region, but do you see now why this is more complicated? Yeah. You will have to use this sometimes to distinguish whether something is ortho or para, or even to distinguish whether there's a double bond. But for now, you're only really looking for the functional group region. Okay. So anybody have a guess for A, what they think that one is?
I thought maybe acetaminophen, but I wasn't sure.
What made you think it was acetaminophen?
Well, it had a really sharp C double bond O curve,
Mhm.
and then it had another sharp curve at 3,000, which I had thought could have been a NH group, but it doesn't really twin peak
So that's
the way that
right
the other
in the
one
space
does.
where an OH would typically
does.
show up, and it's not.
So,
So couldn't that be aspirin too then? I mean,
I'm
not
not
aspirin,
sure
ibuprofen.
what that could be, if I'm being honest.
It could be, but there's other things that help you distinguish what this one is. Honestly, the fact that this one has not much else means that the only thing you're going to find in this molecule is a C double bond O, and everything else is going to be carbons and hydrogens, maybe a nitrogen, maybe an oxygen, but Cam McConnell, do you think you have a guess?
Is it the ethyl butyrate?
Yes, that is ethyl butyrate. Now, this sharp thing right here, that is going to show up in every single IR. It's dwarfed by the OH sometimes. This is going to show up every time because this is simply carbon-hydrogen stretching. It's carbon-hydrogen single bond stretching. When you have an OH, that gets pulled into the OH peak, and so you kind of lose it a little bit. But if it's just this peak right here, this is characteristic of CH stretching and bending. All right, so if A is ethyl butyrate and C is ibuprofen, what do we think B is?
I have two options for that one. I have either aspirin or caffeine.
Aspirin or caffeine. One of those two is correct.
I have caffeine, and my reasoning behind caffeine were the two twin peaks, which would be the NH2s, and then that pointed me towards caffeine.
Very good. So A is ethyl butyrate, B is caffeine, and C is ibuprofen. So one of the things I would like you guys to do as you start working on, well, let me put it this way. Do yourself a favor and don't start chapter 13 homework right now. It will not help you to struggle through it right now. What will help you is working through this part of the IR packet, okay? So I'd like you to work through that a little bit, and then we can check answers when we come back together on Wednesday, or you can ask Wednesday or something else. I do want to talk through one more thing before I let you guys go today. So if y'all want to mute your microphones so I can share my screen again, we will talk about ultraviolet visible spectroscopy. That one. Okay. So I know I'm kind of skipping around in this chapter, but it is mostly because some of this takes a little bit more time to get through than others. So I don't want to start NMR today. I'd rather let IR sink in a little bit. But because it's used less frequently, I do want to talk a little bit about UV vis spectroscopy. Okay, so UV vis is useful for probing electron distribution. So while IR was useful for finding functional groups, UV vis is especially important for finding how electrons are distributed across a molecule. So think conjugated versus isolated and cumulated double bonds, that kind of stuff is useful in UV vis. It is particularly useful for identifying conjugated pi systems. Like in benzene or in other molecules that we'll see here in a second. Much greater energies separate electronic states than vibrational states. And so the energy required to promote one electron from the ground state to another state lies in a higher energy region, which happens to be the UV vis region. So ultraviolet and visible region. In UV vis, your spectra are absorbance versus wavelength. And it always goes from low wavelength to high wavelength. At 400 is the transition from UV to visible. So 200 to 400 is UV, and visible light is 400 to 800. Instead of calling these things peaks, we call them bands. And this is a little bit weird, I know, but this absorbance measurement here is a measure of how much the radiation that passes through that sample is absorbed. So high absorbance means that a lot of it has been absorbed, whereas a low absorbance means not as much of it has been absorbed. To correct for concentration and path length, we can actually convert our absorbance measurements to concentration using Beer's law. So if you remember from Gen Chem, Beer's law is A equals EBC, where A is your absorbance, B is your path length, which is usually 1 centimeter. And that's simply the length of the cuvette that your light has to pass through to get to your sample. And C is concentration. So you can tell how much of a sample you have based on its absorbance. The thing that I haven't defined yet is E. E is the molar absorptivity. And this is specific to a particular molecule at a particular wavelength. So you'll sometimes see these as E450s or E320s because that's the wavelength that they are reading at. Absorption of UV radiation excites an electron from the HOMO to the LUMO. So this is a pi to pi star transition. And you'll remember when we talked about molecular orbital theory that it was unlikely that something would go from the HOMO to the LUMO. But when you have the right wavelength of light, it will jump to a different LUMO. The energy gap varies with the substituents on the double bond. And what you'll remember from doing a lab last semester, do you remember doing the carotenoid lab where I made you crush up those orange seeds and extract something out of them? That was a colored compound, right? Most things that show up in UV vis are colored to your eyes because they're in visible light. So remember when I said that this was called a band, not a peak? This is also called the max absorbance point, and that is related to the maximum wavelength at which it absorbs at the maximum absorbance. If I have, for example, ethylene, its maximum wavelength is 170, which is not even in the UV visible spectrum. But if I have more substituents on it, I now start increasing my maximum wavelength. So this is where a peak would show up or a band would show up. If I have a conjugated diene, for example, with no other substituents, that's now going to lie in the UV visible range. And if I start adding substituents to that, it's going to increase its maximum absorbance. You can keep doing this until you get to the point where you have too many carbons and not enough double bonds. But what you can see is the more substituents on your double bonds, the higher the maximum wavelength, and the more it's going to shift into the visible range. Many organic compounds that are colored at room temperature are colored that way because their HOMO-LUMO gap, this gap here, is small enough that its maximum wavelength lies in the visible region. And that's why they're colored to you. Okay. That's all I want to cover today because I know this is new. I know it's a lot. We are going to start into nuclear magnetic resonance on Wednesday. And that one's going to take us probably Wednesday and Friday to get through because it's more complicated and there's more things to look for than just functional groups. But before we all go, I want to ask, first of all, is there anything that we can be praying for specifically for your family or for people you know, especially in this time? Is there anything we can be praying for? No? Please don't hesitate to send me prayer requests as we're going through this time of uncertainty. I know that this is new to all of us. I know it is hopefully never going to happen again in our lifetimes because I don't know if I can handle 18 months of quarantine right now. I really don't. I don't know if I can handle 8 weeks. I've been on quarantine for a week since we got back from Poland and I'm about to go nuts. So seeing all of your faces has helped greatly. Thank you for being here this morning. And this lecture is recorded, so I will put it up on Canvas in that lecture recordings section. So you can go back and look at things if you need a refresher on something, or if I said something weird and you want to make sure you got it right in your notes, that will be available for you. I'm so proud of you guys for picking up class like you have and running with it. I know this is not how you wanted to finish the semester, Katie, particularly for you. I know this is not how you wanted to finish your senior year, but we're gonna make it through, okay? I promise, I'm here for you guys. I do have office hours specifically for you guys. So I believe that's sometime this afternoon and sometime tomorrow morning. Look on Canvas, it's on there somewhere. I will post daily stuff through the announcements, and I will send emails. I will make sure that you guys have everything you need. If I'm missing something, please tell me, because I may put it on Canvas and forget to make it so that you can see it. Just tell me if something's missing. Anybody have questions about what we went over today? Anything that's due today, lab today?
What's due today?
What's due today? Does anyone want to help Isaac out? What's due today?
Okay, that's how I figured.
Nothing's due today. When is your lab due?
Wednesday at midnight.
Yes, Wednesday at midnight. And there's 4 separate drop boxes for each of the 4 sections of lab. I know, Cameron McConnell, you were having trouble with one. Check it again today. If it's not fixed, let me know, and I'll see what I can do to get you through to the next part. It looks like it was just a glitch in the system, that it was missing that little plus button. So go back and give that a try today and see if that works. Any other questions?
So is there any like post lab that we have for that sort of thing?
Nope, not for this one.
Sorry, is there any other like post lab that we have for? No? Okay. Sorry,
No.
my internet connection's awful.
That's okay. Not for this one, no. Anything else?
What are we planning to do about our old labs that we haven't turned in yet?
I don't know. I haven't figured that out yet.
Okay.
Which ones haven't you turned in?
The electrophilic one and then the acylation alkylation ones, but I know some of us didn't get to acylation.
Everybody's finished with the electrophilic one, right? Electrophilic aromatic iodination. Everybody has at least some sort of results. Okay, go ahead and write that one up just like you normally would. And then what I'll have you do is use something like Adobe Scan and scan pictures of your notebook for me. And then I'll give those to Graham and Drake and Sean to grade, just like they normally would. And then that'll be kind of your last actual lab report for the semester, because everything moving forward from here will be a little bit different. For the Friedel-Crafts alkylation and acylation, we're just gonna call that one a wash. Because it didn't work anyway, so it's fine. Any other questions? All right, in that case, I hopefully will see you all on Wednesday or at office hours tonight or tomorrow. And if you want some extra one-on-one help, feel free to email me. I'm happy to meet with you, and it would obviously be through something like Zoom because you can't come over, unfortunately. And if I could, I would send you all cookies virtually to make your day better, but I can't do that either. So I'll have to come up with something creative, but I don't have creative right now. I have surviving right now. So I love you guys. I'm proud of you. Please stay healthy. Please stay safe. Please be smart. Don't be like the other idiots on our planet. There's a lot of them. So please be smart. Keep yourself safe because I want to see you back next fall in person. Okay? None of this more online crap. Okay? Deal? All right. I will see you guys all on Wednesday. Bye.